and welcome to the 14th lecture in this series. So I'm going to talk about tangent vectors and tangent spaces eventually on manifolds, but to begin with, let's look at the case of Rn as a manifold. So given a point in Rn, it's natural to think of a tangent vector at Rn at that point as any direction with the starting at that point. But so here let me redraw this picture. So given a point P, tangent vector would be just schematically one would draw it as an arrow based at P, but really V is just any element of Rn. Of course, the key point here is that this point P is being thought of. The point is that Rn has two kinds of structures. One is as a manifold, or even more basically a topological space. If you think of Rn in that way, then an element of Rn would be called a point. On the other hand, Rn is also a vector space, and from that point of view, an element in Rn would be a vector. So in this setting, I have a point P and a vector V, and where V is what we would call a tangent vector at P. But this is not a this is not a formal definition of a tangent vector. In fact, to formally define a tangent vector, what we do is the following. So let's, as before, let C infinity Rn denote the set of C infinity functions from Rn to R. From Rn to R. And C infinity Rn is a vector space over R. So given any two C infinity functions, I can take scalar multiples and add them up. And then we define corresponding to every V, which is now thought of as, which is still an element of Rn, but now thought of as a vector, as an element of a vector space. I define TV from C infinity Rn to R as essentially the directional derivative of f along the direction V at the point P. So which we have denoted in my earlier lectures by V of f, and by definition that's equal to the usual derivative of f when I restrict it to the straight line which starts at the point P in the direction V, namely P plus TV. So when I restrict f to that, I get a function of one variable, namely t, and I take the derivative of that. By chain rule, that's also equal to, well, not yet. We saw that this is equal to the derivative, the differential of f as a linear transformation acting on V, and that's in fact equal to the differential is just given by partial derivatives. So therefore, I have the last expression here. Okay, so the main thing is that we'll need the other expressions, but what we have to keep in mind is this T of f is TV acting on f is the directional derivative of f along the direction V at the point P. Now, if we think of TV in this fashion as a linear transformation from C infinity Rn, as a map from C infinity Rn to R, then TV is linear. In other words, TV of C1 F1 plus C2 F2 is C1 TV F1, etc. And this follows immediately from this this thing here. The definition of the directional derivative will immediately give the first linearity, and that will also tell us that TV is TV satisfies the Leibniz rule, the product rule for functions. In other words, the directional derivative of a product is given in the expected way like this, what I have here. So, in summary, for each V in Rn, we have a map TV C infinity R into R, which is linear and satisfies the Leibniz rule. Let us call such a map as a derivation on C infinity Rn. So linearity and the Leibniz rule, anything satisfying that we'll call it derivation. So the main idea here is that instead of talking about V in Rn, we would like to talk about these TVs. So in other words, we would like to say that corresponding to every derivation is essentially of the form TV and for a unique V. So we would like to regard all this property shows that corresponding to every vector I get a derivation, but we would like the converse as well. So that's the theorem here. Let T from C infinity R into R be linear and satisfy the Leibniz rule, which I have again written down. Then the claim is that T corresponds to the directional, T is actually equal to the directional derivative of exactly one vector V in Rn. So this sets up a bijective correspondence between between Rn and derivations on C infinity Rn. Now one thing which we have to note here is that the C infinity Rn is not a finite dimensional vector space, since we can find linearly independent sets of arbitrarily large size. So one can just take monomials, and one knows that if it's not a finite dimensional vector space, if one starts with something which is a vector space which is not finite dimensional, then linear maps on such a vector space is also not finite dimensional. However, this condition we are looking at not just linear maps, but linear maps satisfying this very special property of Leibniz rule. This severely cuts down on the number of maps, and as it turns out, that is the content of this theorem, that the set of derivations is in bijective correspondence with Rn. So let's prove this. The proof is essentially hinges on the following crucial lemma. So the lemma is the following. Given any C infinity function on Rn, we can find n C infinity functions g1, g2, gn such that f of x minus f of p has this form: x1 minus p1 times g1x plus xn minus pn gnx. Here, of course, as usual, this xi denote the coordinates of x and pi denote the coordinates of p, such that this, there is another, so that two things happen. One is this, the second thing is gi at p is del f by del xi at p for all I. So this is a sort of like a Taylor's expansion for f around the point p. It's not really the usual notion of Taylor expansion, but something analogous to that. And this is the main property. So let's see why, if we have this lemma, we'll get the result that every derivation is actually a directional derivative. So assuming the lemma, we proceed as follows. So I'll prove the lemma once we are done with the proof of the main theorem. So we start with a derivation and a function in C infinity, an element of C infinity Rn. So we apply the lemma to this function f and we get n C infinity functions g1, g2, gn on Rn such that we have this expansion and the values of the gi at p are given by this. So let's call this a star, this thing, this equation as star, and by star, now I'm going to just act t on both sides. T of the left side equals t of the right side. Here what we have to, this f, each of these terms here, this x1 minus p1 times g1x, etc., it's a product of two functions. So I can this define a function phi x is xi minus pi. If I define such a function, then f of x minus f of p as the form phi1x g1x phi nx gnx, and I act on both sides. So here I've not, in this what I've written down already, I've not used the phi notation. I've just written it as x1 minus p1, xn minus pn, etc. So now using linearity, I'll get two terms on the left side where this f of p is regarded as a constant function. It's a constant map. So this minus this, and here I'll get n terms when I use the sum. Then I'll be using Leibniz rule on each of these n terms. As I wrote on the left side, I have a product. So, and then I can use Leibniz rule, t of phi1 x, for instance, the first term will look like this. So it would be phi1p t of g1 plus phi2 g1p t of phi1. Now the thing about this phi I functions is that, note that phi I at the point P, phi I, after all, phi I x is xi minus pi, just the difference of the ith coordinates. So when I plug in x equals p, then I just get 0. So that implies that this term doesn't even make an appearance. So what I'm left with is just this g1p times t of phi1. And that's what I've written here. T of x1 minus p1 times g1p, etc. Now here on the left side, we have, in order to get rid of the second term T of constant, we have to make a small observation that if we have any derivation, then T of the constant function c is 0, where c is any constant function. And this is seen, this follows immediately from the Leibniz rule. So I start with the Leibniz rule in general, and let's take f and g to be the constant function 1. That would imply that T of 1, so here I'll get 1, here I'll get 1, so T of 1 is 2 times T of 1, therefore T of 1 is 0. Of course, if T of the constant function 1 is 0, T of any other constant function is 0 by linearity. Now, so the small observation here, this thing here will imply that the second term T of fp goes away. So T of f would be equal to all this right hand side. We can also simplify the right hand side a bit more. Namely, we know exactly what G1p, G2p are. The lemma tells us that GIP is del f by del xi at p. Therefore, I can write T of f is T of x1 minus p1 del f by del x1, etc. Now, given the point p, these are just some numbers that we get, and of course given the point p and the derivation t, I get some numbers. C1 equals this, Cn equals this. So let's define, so what I'm doing here is that I'm defining this C1, C2, etc. Once I have that, then I just rewrite it as T of f is C1 del f by del x1. So what we have done is, we have essentially shown that we started with an arbitrary derivation. We have just shown that it's a linear combination of partial derivatives, purely from the algebraic properties of linearity and Leibniz rule. And once we have this, then we are essentially done, because this is nothing but, in fact, I don't have to write this at all. So at this point, I can just say that this is this thing on the right hand side is exactly TV of f, where V is C1, C2, Cn, because remember that the directional derivative of V of f along the direction V was exactly this expression here, as I had written earlier. So I'm talking about this last part here. So this is what I'm using. So we found a V, starting with an arbitrary derivation, we found a V such that Tf equals Tv of f for all f. There was no assumption on f. And of course, it should be noted that this V, as I said earlier, is determined once you know what t is, once you're given t and the point p. F, obviously f should not play a role here. And the next thing is to observe that this V is unique. This is almost immediate from what we have discussed so far. So I cannot have Tf equals Tv as well as equal to Tw for two different vectors. The reason is that if Tv equals Tw, for some V and W in Rn, then V necessarily has to be equal to W. And the reason for this is that if you can recover the coefficients of the vector from the directional derivative operator just by acting the directional derivative operator along these coordinate functions xi. So TV of xi, again all I'm doing is I'm just using this way of looking at the directional derivative. So if f equals xi, only the ith term will survive, all other partial derivatives will be 0. Therefore, I get the coefficient. And the ith term will survive and it will be just equal to Ci. So here it's Vi equal to TV xi equal to TW xi equal to Wi. In the previous thing, I put V equal to C1, C2, Cn. Here I am using the coordinates of V to be V1, V2, Vn. I mean, it's not that important. The point is, the coordinates of the vector can be recovered by knowing the directional derivative operator. All right, so that proves what we wanted. So that we have set up a correspondence between derivations, a bijective correspondence between derivations and elements of Rn. So, but that still leaves the lemma, which I'll prove now. So I'll start with a C infinity function. The goal is to find G1, G2, Gn such that, and I'm of course given the point P. So goal is to find G1, G2, Gn with the appropriate equations holding. So to define these GI functions, you start with any point x in Rn, and then what I'll do is look at the straight line sigma t joining, so there's no need for this bracket. Let sigma t be the straight line joining x and p. So it's going to start when t is 0, I'll start at p. When t is 1, I'll end at x. Let me define another. So this is a map from, sigma t is a map from the real line to Rn. Now I'm going to compose this sigma t with f. So in other words, restrict. F was already a function from here to R. So this entire thing is Rn. I'm going to restrict f to this line. So f of sigma t, which has this form. If I take the derivative of t, phi, I'll just get chain rule tells me that there's a composition of two functions. So chain rule tells me that it is derivative of f at sigma t acting on sigma prime t. And again, writing it out in coordinates will tell me that it has this form. Now let's integrate. Now that I know derivative of phi, let's use the fundamental theorem of calculus and integrate out this. So when I integrate this between 0 and 1, I'll get phi of 1 minus phi of 0. But as we observed, when t is 1, sigma t is p. No, sigma t is x. The line is ending at x. So, and when t is 0, I get p. So I just get this f of x minus f of p. On the other hand, no, this is not the LHS, this is the RHS. The right hand side is given by, I just integrate out all the n terms here, and note that this each term is a product of two things. One is this partial derivative evaluated at sigma t. The other term is xi minus pi. Well, the xi minus pi don't depend on t. So I can put it outside the integral sign like this and just integrate out this partial derivative. And I do this for all n of them. And this is what I call g1x, g2x, etc. These things here. It's not apparent from the way it's written that where the dependence on x is coming from. But it's clear if you remember that sigma t is the straight line joining p and x. Or rather, more explicitly, sigma t is in fact given by this formula. Tx plus 1 minus t times p. So here the dependence on x is clear. So that's what I'm plugging in this. So here it is 0 to 1, del f by del xi at dx plus 1 minus t times p dt. And finally, the last statement about gi was that gi at p equals del f by del xi at p. And that's clear because when I plug in x equals p here, then this I just get, well, tp and minus tp cancel out and there's a p here. So I just get del f by del x at p. So the dependence on t goes away. So I can put it outside the integral sign and integrate consider 0 to 1 dt, which is 1. So I end up with this. So that proves the lemma, and therefore we have the theorem as well, that every derivation is actually the directional derivative of a unique v in Rn. And we'll use this to, this is going to be the motivating sort of motivation behind defining tangent vectors as derivations on manifolds. So we'll stop here. In the next class, I'll see how all this can be transferred to a manifold. Okay, thank you.